Hi everybody, welcome to my channel Mooniverse. Today we are going to see about the data representation and the number system which is used to represent the data inside the computer. Come on, let's get into the video. So now we can see what type of data can be stored inside the computer. So it can be the numerical data which contains the basic number system, that is the decimal number system what we are using, or it can be the alphabetical data ranging from A to Z and its combinations, or it can be an alphanumerical data, which is the combination of this alphabet and the numeric data. And you have to make a note that it will be also including the symbols, special characters, etc. And one more thing, not only these type of data, but also the computer can store this audio and video representations and other data. But the thing is, all these data can be stored in the form of zeros and ones. So we can consider if it is a numerical data, any of the digits, it can be the representation of a combination of zeros and ones. Or if it is an alphabetical data, A, it will be also a combination of 0 and 1. So now we can see the classification of number system. Usually, the number system is classified into two types. The positional, or we can call it as the weighted number system. And this weighted number system, no, it is having weight for each digit, which is determined by the base or radix. For example, when we consider the decimal number system, deci means 10, right? So this number will be given the weight based upon the base, which is 10. And non-positional number system, this is generally used for shift position encodes and for error detecting purpose. So we can see in the later on lecture videos. So now we can see how the inner classification of this positional number system and the non-positional number system exists. Usually the positional number systems consist of the decimal, octal, binary. Binary can be the BCD code or 84214 code. And it also includes the hexadecimal codes. Coming to non-positional number system, it contains XS3 codes, cyclic codes, Roma code, Gray codes. Hope some of these codes you might have gone through while you're learning some of the syllabuses. So the common number system used in the computer or the decimal number system, binary number system, octal number system, and the hexadecimal number system. So now we are going to see what these number system shows their numbers of. So now we can see the number system in detail. Usually a number has a base and its position. Usually the base depends upon the type of number system what we are using. In common, we are using a decimal number system for which we are having the base as 10, and for octal it is 8. Usually for a number system, when the value is not specified, that is the base value is not specified, it is considered as a decimal number system. And coming to the position, um, actually the position starts from the right hand side of the number. That is, for a number 52, it will be starting from 2 and then from 5. And the starting value will be 0, 1, and it will be continued as it move on. So now we can see each digit, that is in 52, 2 is a digit and 5 is another digit. So each digit is having a face value and the position value. So we can consider the same example. The face value is 5 and 2, and the position value, as we said in the above consideration, it starts with the right hand side. So it is starting with the right hand side. The first position is 0 and the second position is 1. And this each number, that is the each digit, can be represented by its base and its position, we can say. So now we can see how the value 52 is being represented. So it is basically a decimal number. So its base value is 10, right? And the position of 2 is 0 and 5 is 1. So how we are going to calculate the number is the 2, that is the number in the position 0, is multiplied with the decimal representation 10, that is the base value, to the power of its position 0. So 2 into 10 to the power 0, and for 5 the position is 1, so it is 5 into 10 to the power 1. Now it becomes 5 into 10, and any number to the power 0 is 1, so 2 into 1. So now it becomes 50 plus 2, 52. This is how we are going to calculate a single value depending upon the number system what we are considering. So now we can see the base representation of different number systems. For the decimal number system, deci, which means 10, so the base is 10. For binary, bi is 2, and octal is 8, and hexadecimal, hex stands for 6, and decimal, deci stands for 10. So 10 plus 6, the base is 16. So now we can see how we are going to represent the number. So the number, to the base of it, it should have the base representation. So here are two examples. A decimal 23 can be represented as 23 to the base 10, and for an octal 345, it can be represented as 345 to the base 8. Now we can see about the decimal number system. Deci means 10. So it defines what the number system is. So it is the combination of 10 numbers which varies from 0 to 9. Right? So now we can see some examples. This is a decimal number, 5768 for 2341.678. Now we can see how the positional value and the quantity of this number can be defined. So imagine a number with 4 digits. So let us consider the same example over here, 2341.678, right? So the position of this 1 is 0. So as we saw, it starts from the right for a number which is heading before the decimal point. So 0, 1, 2, 3. Likewise, the position moves on for a higher digit number, right? And after the decimal point, it starts with the value -1. So 6 is with the position -1, 7 is with the position -2, and 8 is with the position -3. So how can we define the value of these positions? The positional value. The positional value is defined by means of the exponential value of 10 because it is a decimal number. That's why here we are putting 10. 10 to the power 3, the position comes here. 10 to the power 2, 10 to the power 1, and 10 to the power 0. Likewise, after the decimal point, 10 to the power -1, 10 to the power -2, and 10 to the power -3. This also can be represented 10 power 3, that means thousands. The positions can be thousands, that is 3000. We'll be calling the value as 2000, right? 2341. Likewise, after the point, it can be 10 power -1, that can also be redefined as 1 by 10, and 10 power -2 as 1 by 100, and 10 power -3 is 1 by 1000. Now we can see for the binary number system, as the name specify bi, it is represented by 2 different digits. The digits are zeros and ones. So all the numbers of this particular binary number system will be the combination of the zeros and ones. We can see the example. Usually this will be written inside the bracket with the base value 2, right? So now we can see the position and positional value of this one. So here also the position will be varying from 0, 1, 2, 3, and after the decimal point, the positions will be starting from -1, -2, -3. And we have to note to a point that the positional value will be the exponent of 2 as it is a binary number system, right? So 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. And after the decimal, it comes 2 to the power -1, -2, and it will be going on. So this can be represented by the quantity as 1, 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. Likewise, after the decimal, it is half, quarter, and 1/8. Likewise, it will be moving on when we are putting more number of digits after the decimal points. Now coming to the octal number system, oct means 8, right? So here 8 numbers will be used. That is 0 to 7. Totally 8 numbers are used here. And let us see the example. 274-103-2375. You have to make sure, or you have to check out these values, that here are no numbers which are exceeding 7, right? Here also the same consideration, it will be written to the base of 8. All the numbers will be having the base representation. Only the decimal numbers will not be having. If it is not having, it will be considered to the base 10, right? So now here the position, as it is an octal number system. Oct means 8, right? So all the exponentiation will be towards this 8, right? So as we have seen for the previous number system, 8 power 0, 1, 2, and likewise it's moving on. So 8 power 0 is 1, 8, and 2 is 8 power 2. That is 8 square is 64. And also that after the decimal value, it will be 1/8, 1/64, and it will be going on like that. So now we can go for hexadecimal. Hex means 6 and decimal means 10. So 10 plus 6, it is 16. So it will be a combination of 16 numbers. So the 16 numbers will be from 0 to 9. Totally we are having 10 numbers, and we are having 6 other codes which are varying from A to F, right? So 10 plus 6, totally 16 codes will be used here. So we can see the representations. For A, it is 10. Okay. For A, it is 10. And for B, it is 11. C, it is 12. D is 13. E is 14. And F is for 50, right? So all the numbers which are represented for hexadecimal will be a combination of these 16 numbers. So here, either we can specify as H or we can specify as 16. To the octal number also, we can specify as O to the base, right? And now we can see, as it is a hexadecimal number system, the exponential positional value, all the values will be to the exponentiation of 16, right? So in summary, let me show you the decimal value, which is having the base 10, and the binary value is having the base 2, octal is 8, and the hexadecimal is 16. This is actually the consolidation of this entire session videos. And this is the number ranges for each number system. 0 to 9, that is total count is 10. And for binary, it is 0 and 1. And for octal, it is 0 to 7. And for hexadecimal, it is 0 to 9. And it will be including the alphabetical values from A to F, which is varying from 11 to 50, right? So these shows the last digits. So thank you. Thank you for watching my slides. In the upcoming videos, we can see the number conversion between these number systems. Thank you.